The idea of time travel has always fascinated humanity. From H.G. Wells's The Time Machine to the adventures of Doctor Who, we've been captivated by the idea of journeying through time. But could time travel ever be more than just a fantasy? Could it be a real possibility hidden within the strange world of quantum mechanics? For centuries, time was seen as absolute and unchanging, a river flowing steadily from past to future. Then came Albert Einstein, who revolutionized our understanding of time with his theories of relativity. Einstein showed us that time is not absolute but relative, a concept that opened the door to the possibility of time travel. Today, physicists are exploring the even stranger world of quantum mechanics, where particles can be in multiple states at once, and information seems to travel faster than light. Could these bizarre quantum effects hold the key to unlocking the secrets of time travel? Let's take a journey into the realm of quantum mechanics and explore the mind-bending possibilities it holds for journeying through time. To understand the possibilities of time travel, we must first delve into the very nature of time itself. We first need to grasp the fundamental concepts laid out by Albert Einstein's groundbreaking theories of relativity, which revolutionized our understanding of the universe. Einstein showed us that time is not a rigid, unchanging backdrop to the universe, but rather a flexible fabric woven together with space, creating a dynamic entity. He called this fabric space-time, a concept that intertwines the three dimensions of space with the fourth dimension of time. Imagine space-time as a giant trampoline, where the surface represents the fabric of the cosmos. Massive objects like stars and planets create dips in this trampoline, much like bowling balls would if you placed them on the trampoline's surface. These dips represent gravity, bending the fabric of space-time. Einstein realized that gravity isn't just a force, it's a curvature in space-time, altering the path of objects and even the flow of time itself. Here's where it gets really interesting. The stronger the gravity, the slower time flows. This phenomenon is known as gravitational time dilation. This means that time passes slightly slower at sea level on Earth than it does in orbit, where gravity is weaker. The difference is minuscule but measurable. This effect, called time dilation, has been experimentally confirmed and is even factored into the GPS systems we use every day, ensuring their accuracy. Einstein's theories also suggest the possibility of wormholes, theoretical tunnels that could connect distant points in space-time, offering a potential shortcut. Imagine folding our trampoline in half so that 2 points touch. A wormhole would be like a shortcut through this fold, allowing us to travel vast cosmic distances in a much shorter time, bypassing the conventional limits of space travel. However, the existence of wormholes remains purely theoretical, a tantalizing possibility yet to be proven. While Einstein's theories provided a framework for understanding the nature of time, quantum mechanics throws a whole new set of mind-boggling possibilities into the mix. Quantum mechanics governs the interactions of particles at the atomic and subatomic levels. And it's a realm where the rules of classical physics seemingly break down. One of the most bizarre concepts in quantum mechanics is superposition. Imagine a coin spinning in the air. It's neither heads nor tails until it lands. In the quantum world, particles can exist in multiple states simultaneously, much like our spinning coin. It's only when we observe them that they collapse into a single defined state. Another strange phenomenon is quantum entanglement. Imagine two coins flipping in perfect unison even if they're miles apart. In the quantum world, entangled particles are linked in such a way that they share the same fate, no matter how far apart they are. If you measure the state of one entangled particle, you instantly know the state of the other, seemingly violating the limitations of the speed of light. Now let's dive into the even stranger territory where quantum mechanics and time travel intersect. This is a realm where the boundaries of time blur, and the future and the past can seemingly interact in ways that defy our everyday understanding. One mind-bending concept is the quantum time loop, where a particle travels back in time to interact with its past self. This isn't just science fiction, it's a theoretical possibility that challenges our conventional notions of cause and effect. Imagine a billiard ball traveling on a loop-the-loop track. As it moves, it follows a predictable path, looping back to where it started. In a quantum time loop, a particle essentially travels on a similar loop through time, influencing its own past behavior. This self-interaction can lead to outcomes that seem paradoxical, but are mathematically consistent. This concept, while strange, is consistent with the laws of quantum mechanics. The equations that govern the quantum world allow for such peculiar scenarios, even if they seem impossible from a classical perspective. Even more bizarre is the idea of retrocausality, where an event in the future can influence an event in the past. This flips our usual understanding of time on its head. Think of it like this. Imagine receiving a letter today that influences a decision you made yesterday. It's as if the future is reaching back to alter the past. While this seems illogical, some interpretations of quantum mechanics suggest that retrocausality might be possible. These interpretations challenge our linear view of time and open up new possibilities for understanding the universe. One famous thought experiment that hints at retrocausality is Wheeler's delayed choice experiment. This experiment explores how our choices in the present can affect the past behavior of particles. In this experiment, a photon, a particle of light, is given a choice to behave as either a wave or a particle. The decision on how to measure it is made after it has already passed through a slit. The experiment demonstrates that the choice we make about how to measure the photon in the present can seem to influence its behavior in the past, suggesting a form of retrocausality. It's as if the photon knew how we were going to observe it and adjusted its behavior accordingly. This challenges our understanding of time and causality in profound ways. The possibility of time travel raises a host of paradoxes, the most famous of which is the grandfather paradox. Imagine traveling back in time and, well, accidentally killing your own grandfather before your parent was even born. This would create a paradox, as you wouldn't exist to travel back in time in the first place. The grandfather paradox highlights the potential contradictions that time travel could create. So, how does quantum mechanics address this conundrum? One intriguing possibility is that time travel might not lead to a single, fixed timeline but rather to a multitude of parallel universes. Section 6. Parallel universes. A quantum solution to time travel paradoxes. The many worlds interpretation of quantum mechanics suggests that every time a quantum measurement is made, the universe splits into multiple parallel universes, each representing a different possible outcome. In the context of time travel, this could mean that instead of altering the past in our own timeline, we might be creating a new, branching timeline. So, if you were to travel back in time and prevent your grandfather from meeting your grandmother, it wouldn't erase your existence. Instead, you might find yourself in a parallel universe where you were never born, while your original timeline would remain unchanged. The concept of parallel universes is still highly speculative. However, it offers a fascinating potential solution to the paradoxes of time travel, allowing for the possibility of changing the past without creating logical inconsistencies. Section 7. Building a quantum time machine. Dreams versus reality. While the idea of quantum time travel is captivating, turning theory into reality is another matter entirely. The technological challenges of manipulating space-time and harnessing quantum effects for time travel are immense and likely far beyond our current capabilities. One of the biggest hurdles is the sheer amount of energy that would be required to create wormholes or other space-time distortions. We're talking about energy levels far exceeding anything we can currently generate. Additionally, we would need to develop a deep understanding of how to control and stabilize these distortions so that they wouldn't collapse before a time traveler could pass through them. Another challenge lies in the unpredictable nature of quantum mechanics itself. Harnessing the inherent randomness of quantum events to create a reliable means of time travel would be a monumental task. It's important to remember that just because something is theoretically possible doesn't mean we have the technological means to achieve it in practice. Section 8. The Quest for Quantum Time Travel. Current Experiments and Future Hopes. Despite the challenges, physicists around the world are actively exploring the boundaries of quantum mechanics and its implications for time travel. While we haven't built a time machine yet, exciting experiments are shedding light on the bizarre connections between quantum mechanics and time. For example, researchers are investigating the possibility of creating closed, time-like curves in the lab, tiny loops in space-time that could allow particles to travel back in time. While these experiments are still in their early stages, they represent a significant step towards testing some of the more exotic predictions of quantum mechanics. Other experiments are exploring the relationship between quantum entanglement and time, searching for any hints that information might be able to travel backward through time. While the results are far from conclusive, these experiments push the boundaries of our understanding and keep the dream of time travel alive. Section 9. Time travel and the meaning of time. A final reflection. The quest to understand whether time travel is possible goes beyond simply satisfying our curiosity. It touches on the very essence of what it means to be human, to wonder, to dream, and to explore the unknown. It has profound implications for our understanding of the universe and our place within it. The idea that we could move through time as we do through space opens up a realm of possibilities that challenge our current scientific paradigms. If time travel were possible, it would challenge our most fundamental assumptions about causality, free will, and the nature of reality itself. It would force us to rethink the linear progression of time and the interconnectedness of events. The study of quantum mechanics and its relationship to time travel is still in its infancy. Yet, every discovery brings us a step closer to understanding the true nature of time and its potential malleability. We are like explorers charting a vast and uncharted territory, filled with strange and wonderful possibilities. Each new theory, each new experiment, is a beacon guiding us through the darkness of the unknown. Whether or not we ever succeed in building a time machine, the journey itself is expanding the horizons of human knowledge and pushing us to confront the most fundamental mysteries of the cosmos. The pursuit of time travel is as much about the journey as it is about the destination. In the end, the quest for time travel is not just about finding a way to visit the past or future, it's about understanding the fabric of reality and our place within it. It's about deepening our understanding of the nature of time itself. Time is a dimension that we are only beginning to comprehend, and its secrets are waiting to be uncovered. And who knows what wonders await us as we continue to unravel the secrets of this most enigmatic dimension. The future holds endless possibilities, and the journey to understand time is just beginning.